channel. So we still continue in the review of the paper, which is the Skip-GANomaly, which we have been looking at for some time now. The Skip-GANomaly, which addresses the anomaly detection problem by using Encoder-Decoder, also with a discriminator. So in this session, we want to focus our attention on the problem formulation, and we look at how the problem is formulated formally, that is to say mathematically. So now we have the input data set. So our data set is split into dtrain and dtest. So dtrn and this also tst for training and test. So we're going to train our model on dtrn, then we test it on dtst. Now the way the dtrn is formulated is such that it's a tuple of instances, and the total number of examples in the dtrn is m, where m is an hyperparameters that we choose. So each tuple consists of x, which is an image, and y, which is a label. And the y represents the y is equals to 0 in all the instances of the dtrn to denote the normal class. So all the instances in dtrn are actually coming from the normal samples. Then the test is also similar formulation. I think they wanted to put n here, so there's an error here. This should have been n, x subscript n. So, and that n could come from the normal or abnormal samples, and the y could be a member of 0 or 1, where 0 denotes normal and 1 denotes abnormal classes. We expect that the number of samples in dtrn, which is m, will be far greater than the number of samples in the test. So what is that's the data set input. So the task is based on that data set. We need an f, a model termed f, that is trained on dtrn, and we evaluate it on dtst. So our objective is our end goal is to get a model f. So, and the training objective depicted by tau of that model help. So what the model is supposed to do to achieve is to capture the distribution of the training within not only image space but also in the hidden latent vector space, which we have explained before. So, and capturing the distribution within both the image space and the latent vector space enables the training objective to learn higher and lower level features that are unique to only the normal images. Excuse me. And what we hypothesize is, our assumption is that the anomaly score, which is also a function represented by this mathematical symbol, based on that training objective tau, will yield a minimum score for the normal sample, since it's been well trained on both the image space and the latent vector space. But it will yield a higher score for the abnormal images, such that a higher anomaly score, when you feed in an x, given a sample x, will actually indicate that x is coming from a distribution of any abnormal with respect to the distribution of the normal. So that's essentially, so we're trying to learn f, which is our model, and dtrn is the training. All right, that's it for this one. Thank you very much, and see you in the next one.